Welcome to the Explainer. So, you know that feeling when you're staring at a massive, chaotic wall of C code, and you're just thinking, how on earth does anyone make sense of this? Well, if you've been there, you are absolutely in the right place. Today, we're demystifying structured C programming. We're going to take that sprawling, messy code and show you how to turn it into a clean, efficient, and super organized program. Honestly, think of this like learning the architectural blueprints for building rock-solid software.
Here's our quick roadmap for today. We're hitting 5 main pillars. First, taming the code chaos. 2, procedures versus functions. 3, passing data and scope. 4, managing multiple items with arrays. And wrapping up with number 5, strings, which are basically a character train. Let's jump right in.
Section 1. Taming the code chaos.
You know, when you're first getting started, it is so tempting to just dump everything into one massive scrolling block of code. But then your program grows, right? It scales from 50 lines to, say, 5,000. And suddenly, debugging it is a total nightmare. So, we have to ask a fundamental question. How do you actually control this code complexity and stop repeating yourself over and over?
The magic answer here is modularity. You simply have to break that giant problem down into smaller, independent, reusable chunks. And the benefits are huge. It logically organizes your code so you can actually find things. It gives you real reusability, meaning you write a task once and you can use it 100 times without copy-pasting like crazy. It also means different developers can work on the exact same program without constantly stepping on each other's toes. And of course, it gives you scalability. Your software can actually grow without, completely collapsing under its own weight.
Moving on to Section 2, procedures versus functions.
Okay, so in C, we organize our tasks using these 2 main ideas, and the difference is actually pretty straightforward. A procedure is just a block of code that does something, like, say, printing a welcome message to the screen. But the key here is it has a void return type. It doesn't hand any data back to you when it's done. A function on the flip side takes in input parameters, crunches some numbers or does some logic, and then actually hands a computed result back to whoever called it.
Let's completely dissect how a C function is built. Starting on the far left, you've got the return type. This just tells the compiler, hey, expect an integer, or maybe a float, or a character to pop out at the end. Next is your identifier, literally just the function's name. Inside the parentheses, you drop your parameters, which are your inputs. And finally, inside those curly braces is where the magic happens. The instructions run, and that return statement fires the final result right back to exactly where the function was called. But, big warning here. C compilers are notoriously strict. You've got to follow the golden rule. A function absolutely must be known to the compiler before you call it. Remember, the compiler reads your file top to bottom. If it trips over a function call it hasn't formally met yet, it's going to throw an error. So, to fix this, you either write out the whole function at the top of your file, before your main code, or you just use a prototype declaration at the top. It's basically a little name tag that says, hey compiler, trust me, this function exists, I'll give you the actual details later.
All right, Section 3, passing data and scope.
To figure out where our variables actually live and how they're shared, we have to look at how data gets passed around. C gives us 2 ways to do this, and they act totally differently. By default, C uses call by value. Think of this like taking a photocopy of your variable and handing that to the function. If the function takes that photocopy and shreds it, no big deal. Your original variable is perfectly safe. It's your secure, everyday default. But what if you actually need the function to update the original data? For that, we switch to call by address. Instead of a photocopy, you hand over the actual memory address using pointers. This gives the function the power to directly modify the original variable. It's incredibly flexible, a real game changer, but man, you have to be so much more careful with it.
And that brings us right to variable scope. So a local variable is declared inside a specific function or even just a specific block of code. Its entire world is restricted to those curly braces. Other functions, they can't see it, and they definitely can't mess with it. Plus, it has a super short lifespan. The exact second that function finishes running, poof, the local variable is completely destroyed in memory. And honestly, this isolation is a fantastic thing. It prevents weird, unintended side effects and keeps your code really secure and predictable.
Now, the polar opposite of that is a global variable. You declare this one outside of all your functions, usually sitting right at the very top of your file. Because it's global, literally any function in your entire program can read it or change it, and it just hangs out in memory until the whole program shuts down. Sure, that sounds really convenient for sharing data, right? But in structured programming, you actually want to avoid global variables as much as possible. If you rely on them too heavily, tracking down bugs becomes an absolute nightmare, because any random part of your code could have secretly changed that variable's value.
Section 4 now, Arrays. Let's talk about managing multiple items. Imagine for a second you need to store the grades for 50 students. Instead of cluttering your desk with 50 loose pieces of paper, arrays let you stash them all in a neat, continuous row of interconnected lockers. It completely eliminates variable bloat, so no more writing grade 1, grade 2, all the way up to grade 50. You just use one single array called grades. Now, standard arrays do have a fixed number of elements, and they all have to be the exact same data type, so no mixing integers and characters, it just won't work. Under the hood, C stores all these items in contiguous memory locations. That means they are physically packed right next to each other in the computer's memory, which is exactly why accessing them is so lightning fast.
Okay, if there's one thing you take away from this, it's this number right here, 0. This is the infamous zero index rule. When you want to grab the very first element in a C array, you do not ask for element number 1. You ask for element number 0. Think of the index as the number of steps you have to take from the very start of the array. To get the first item, you haven't moved yet, so you take 0 steps. Forgetting this rule and starting your count at 1, honestly, it's the single most common mistake almost every single new C programmer makes.
Because arrays hold a bunch of elements in a row, you need a systematic way to deal with them. Say you want to fill up an array with user input. You're not going to write out 50 separate lines of input code, no way. You use a loop. First, you just traverse the array using a standard for loop, which naturally keeps track of your index, right? From 0 up to the size of your array. Second, at each stop along the way, you use a function like scanf, combined with that ampersand address operator we talked about. This grabs the user's input and locks it directly into that specific little memory locker. It's clean and it's incredibly efficient. Finally, Section 5, strings, or as I like to call them, the character train. So we've got numbers figured out, but what about text? Well, in C, dealing with text is exactly like managing a train made up of individual character cars all linked together. Here's a fun fact for you. C actually doesn't have a built-in string data type at all, unlike a lot of newer languages. Instead, a string is quite literally just an array made of characters. But how does the computer know when the word is actually over? It needs a caboose. Every valid C string absolutely must end with a special null character which looks like a \0. So if you type the word hello, under the hood it's really an array of 6 characters, HELLO, and then that critical, invisible null terminator right at the end telling the program to stop reading.
Now, to keep you from having to write custom loops just to count letters or copy a word, C gives you a built-in cheat sheet of string operations. You've got stringlen, which gets you the length of the string, and importantly, it ignores that hidden null character. You've got string copy to quickly copy text from one array right into another, and string compare lets you compare 2 strings to see if they're a perfect match. Trust me, these functions will save you an unbelievable amount of time.
I do have to give you a pretty serious warning here, especially when you start copying strings around. The golden rule is the destination array must be large enough to hold the source string. If you've got an array built for 5 letters and you try to cram a 10-letter word into it, C is not going to stop you. It doesn't hold your hand. It will just enthusiastically keep writing all that extra data straight over whatever innocent variables happen to be sitting next door in memory. We call this a buffer overflow. It is a critical error, a massive security flaw, and honestly, one of the top ways programs completely crash and burn. You've always got to watch your memory sizes.
And that brings us to the end of our explainer. We've unpacked how to break logic down into functions, how to securely pass your data around, how to wrangle items into arrays, and how to link characters up into strings. These 3 pillars really are your absolute essential tools for controlling code complexity. So I want to leave you with a thought. How will you use functions, arrays, and strings to step up and tame the chaos in your next C program? I really hope this explainer gave you the rock-solid foundation you need to start writing clean, incredibly efficient code. Happy programming!